We're going to take a look here at how we can do an integral by using partial fractions decomposition. For this integral here, I first tried a u substitution where u equaled the denominator. Thought that might work, didn't work out very well, and so I abandoned that idea and decided to use partial fractions decomposition. So what I did was I took the integrand, the thing inside of the integral, and I thought that I could break that up into two fractions that I could do this integral in a more efficient way. So to break it up into two fractions, we would have to have a sum that looked like this, as you see on the right. I then performed the partial fractions decomposition process. Please hit pause if you'd like to examine the algebra. And when I was finished, I knew that the original expression could be rewritten as this sum. If this looks very confusing to you, you may have missed my first video on just how this process works. Nonetheless, to avoid the complication of all the algebra here, suffice it to say that these two expressions are equivalent. Again, go back to the video if that's still unclear how that process works. Moving on, the fact that these expressions are equivalent means I can replace the integral of one with the integral of the other. And while this may not seem beneficial at first, it actually is quite beneficial because then I can integrate the sum as the sum of the integrals. And each of these is individually pretty easy to do. I won't show the work here, but for each one I used a u substitution where u equaled the denominator. And after some work not shown here, I have the final answer, and that shows how useful partial fractions decomposition can be when integrating a big ugly fraction.